How important is good antenna design in EW? Now, this is a video that is based on a webinar that I did earlier this week, discussing exactly that, the importance of good antenna design in EW. Now, you don't have to specifically say EW. EW, by the way, for those of you watching this video who don't know what that stands for, it's electronic warfare. Now, that may seem for some people like, wow, that's quite an intense description or something that is not there seen. But you have to think about electronic warfare these days as something that is very relevant, not just in areas of conflict, but also just as much in public safety. Just think about crowd control. When you, for instance, have a sporting event and there's somebody with a drone coming over, that's a stupid idea. So you want to stop this guy from doing that. The same would be in an airport. So you have an airport and then somebody comes with a drone over that, and it basically puts the actual airplane in danger as they approach or as they take off. So that's the same technology. And then the other thing, if you think electronic warfare, also think about radars. Now, yes, of course, again, in areas of conflict, it is a very relevant application. But going back to the airport, if you want to fly, you need to have a radar so that people know where you are, and you in the airplane wants to know where you are as well. So that technology gets used everywhere. So electronic warfare is one word. Good antenna design is the main theme of this just this video, lecture, whatever you want to call it, tutorial. What I'm going to do is just run through a bit of a thinking pattern to explain how I see things, and then also what we can do to hopefully make things better for the general user of this application. I'll not say general public, it could be anybody, but specifically more in the professional world. So first, of course, in this introduction, design philosophy, that's specific to Black Art Technologies and also at RF Shop, but hopefully it is a bit broader than that. Then, of course, the topic for the next section is to say antenna is not a piece of wire. That's something that comes from a previous employer that I had, a comment that I've heard. So I'm saying it's not a piece of wire. You'll see why I say that. The question, what makes an antenna better? What are you comparing with? Why is an antenna better than another one? What's the difference between them? Not going into too much detail. And then, of course, at the last end is just, I would have gone through some fundamentals. How do we apply the fundamentals? Us as Black Art Technologies, new trends that we see, and also there's a thing about simulation, there's a thing about experiments as well. So the value of those two and how they actually work together, and you don't have one or the other, you need to do both. Now, first of all, introduction. So I am currently reading a book from Simon Sinek. Have been actually aware of this for a really long time, and I'm quite excited to enjoy this. The book says simply, start with why. Now, starting with why is a massive thing for me, and it comes to the golden circle that is explained in the book, but also in a TED talk that was done in 2009 already, so it's nothing new here. You need to think to yourself, why am I doing what I'm doing? How am I doing this? What am I doing? Now, I'm applying that logic now on this video as well. So first of all, I'm going to tell you why there is a perception antennas is maybe no longer relevant. So that's something that I'm thinking about, have been thinking about for the last 26 years as I was in the antenna industry already. How can we prove antennas are key, are important, is relevant? And then what are we designing? So I'm just going to go through a few in-house examples. Some of them are the typical YouTube fun ones that we do, and also just one example that's actually being used for a project for a customer as well. Because I do get questions these days because people say, oh, what do you actually make? Because I keep talking about other people's design, or make all these not silly, but you know, more fun type antennas, and I never make or never talk about an antenna that I can do myself. So that's really what this is about. It's just to also just say, well, there's an example of something that can be done using the fundamentals I keep talking about, and it works a treat. Now, right, so next slide, design philosophy. You would hear me a lot in YouTube, and I haven't said it yet on this one, so it's unfortunately on the screen always, but keep it simple. I don't say it just for fun. I don't say it because it's a nice thing to say or it's a catchphrase. I say it because it honestly is what I believe, and I'm pretty sure my kids, my wife, my mum, everybody would say that's how I grew up, and that's what I do. What I do think as well, though, is what I say there: keep it simple and get it right. So when we do antenna design, when you do product design in general, you need to know what is your base baseline and get that right before you go and do all sorts of fancy stuff. It's always tempting to go for the more complicated stuff, for the more innovative stuff, but just get the basics right so that things can work, and then you chip away and make it more complicated. A lot of humans are just tend to say, oh, let's go for shooting for the stars, and then you get nothing, which I agree, there's a good reason to think like that, but always when there's something very instrumental that you need to do, just get something functional so that you know, I'm working, this is going, now move forward a little bit. Now, for antenna design, it's a lot of physics. There's a lot of fundamentals in there. Physics never changes. It's just the way it is. We can't bend the rules of nature. You can do things to make it more efficient. You can do things to make it work more in your advantage, but you can't change the physics themselves. And then, of course, when you do simulations or design work, in our case, specifically with antennas, when things don't make sense, think about what are you looking at. And if it doesn't make sense, maybe there's a reason it doesn't make sense. The thing with software that we're using, simulation software in our field, but in any basic application, if the software gives you something that you just don't expect to see at all, just make sure that you're not either coming across a Nobel Prize of some physics, or you're making a silly mistake and the computer doesn't know how to not deal with it. So it's doing what you told it to do. If it doesn't make sense, the computer's not necessarily going to know. It's just going to run with what it says. This is what I'm told to do. Let me just do this. And then the last thing, keep it real. And I have a few examples here. I did drop this catchphrase from our video because it was just getting a little bit long to say keep it simple, keep it real. But keep it real is very much what I encourage and what I want the team here at RF Shop to also know as well, that sharing experience, as I say, is different to sharing knowledge. Now, you can't say, I know this, I know that, blah, 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 blah. But if you are admitting that, how do you know these things? Sometimes it's because of experience. Experience isn't always pleasant. Like, you could have made a massive mistake. You can either not talk about it and the next person is also going to say a mistake, or you could share what you've learned and kind of learn from it. And if you talk about it, it actually helps others to learn, and it makes you as a human human. So that's what I always do. It's pointless to hide your mistakes because people want to know and they want to actually learn from this. So there we go. I say it actually. Mistakes are made to learn from, not to hide away. Right. So first section, antenna is not just a piece of wire. But the question that I do have, it's a rhetorical question because it just is always going to be the case. Why do we have to talk about it over and over again? It's just going to be the way it is, isn't it? So let's see. Now, a bit of an approach to how I think about this. So bear with me. Every single person is a consumer somewhere in their life. I take myself, for example. If I were to go to Bunnings and I buy myself a power tool, Bunnings, for those who are not in Australia, that's our local mainstream hardware store. If I were to go power tool, I wouldn't necessarily want to go for the high-end Makitas or Milwaukees or those brands. If I just want something for my home use, I'm a consumer. I know what I want. I want it just to get it done, so that's it. So in that regard, I would be a consumer. And it's the same with anything, really, that you can be, all professional consumers versus professionals, but we are all consumers somewhere in our lives. That's just the way it is. And that's also the thing that now drives the antenna world quite a lot, because if you look at antennas, they keep disappearing from our phones. They keep disappearing from our devices. They don't disappear. And I remember this is now the Nokia, I think it was the 3210 back in, giving away my age, but when I was a student. That was the first time that they had this 3210 coming out with no antenna. And it was an awesome marketing experience. I was just impressed myself. This was a really sexy little phone. No antennas. But there is an antenna. It's just hidden inside. You do sacrifice performance. You do complicate things a little bit, but at least the consumer doesn't have to deal with this thing sticking out anymore. And that's just a continuous drive we see going forward more and more and more. Now that I think about this, if you look at automotives, at cars as well, they have little shark fins at the back. No longer this long old whip that came out to get you FM antennas, FM radio. But there is a price, because you do want that big antenna to get what you really need. You get a smaller antenna because the electronics behind it got better. But if you were to combine the bigger original antenna, the external antenna, the visible antenna with the better electronics, you would have actually had a better solution. So it is quite interesting that the consumer world is constantly bombarding us with the fact that there is no antenna because we don't want to see them anymore, because the market told us we don't want to see them anymore. And then that drives the complexity on antennas, that people don't think they are relevant, they're not there, they're not necessary, we can do it all in software. That's something we do. Now, here's two examples just to show the way that things happen for us. First, on the left is a picture created in ChatGPT of a house. And if you could look at all the connected devices, everything is connected some way or another to the other devices. TVs, laptops, phones, tablets, all connected to a router that maybe not even has an antenna. It's all Wi-Fi, magically connected. What I would know, maybe you who watch this video would know, that there is antennas in there. But somebody who's in school, somebody who's who's just not technically inclined or thinking about these things, they just don't see the antenna. So it doesn't really come to mind that there is an antenna available or relevant or necessary. The same is the picture on the right, which is just a shopping mall. Again, ChatGPT. You walk into a shopping mall where, in a network design perspective, it's an absolute nightmare. You have like thousands of people in a very small area. You have walls, you have metal structures, you have obstructions, you have everything there to make it an absolute disaster for a radio network. So they do all these nice integrated distribution networks in there. You have the various networks, you have various access points. The Wi-Fi network, it's, if you were to walk to a convention center and you keep having the same Wi-Fi access or SSID on your phone as you walk from this side through to the other side, it's not the same device. Like, there's a whole mesh there. And all my IT friends would now say, yeah, duh, we know. They do. But consumers don't. And who is a consumer? Anybody who doesn't think that this is important. Because if I were to go to a pharmacy, my wife is actually working at a pharmacy, I'm clueless. I need to know what they tell me. But other than that, I don't know. Ibuprofen or paracetamol. I now know it makes a difference, but I'm not a specialist, and I don't claim to be, and I don't have any knowledge on that. I'm a consumer. Anyway, I think you got the message, I guess. So the problem that brings is that in a team of people, if you're one of these big companies, there's people that are not experts in your field who's going to be involved and potentially driving your project. So let's say on the left I have a program director. It's a high person up there. Comes from a law background, comes from a banking background. They don't see your field of interest, in my case antennas. They don't see the way I see it. They don't look at the house as you drive past and they look at every Starlink dish. They don't notice that. I don't notice law issues. I don't notice well, maybe I do as a business owner now, but I don't see the financial world the way that the banking background people see them. And then the next phase would be, okay, you're a project manager. So you have to go right at the top. He has absolutely no knowledge of anything that relates to the detail of the antenna. He knows what the consumer market tells him, that the phone doesn't have an antenna. At home, he has no antennas. That's it. The next person down is the project manager, somebody who is maybe scientific in background, right? So we now have this whole nuclear thing coming up in Australia, but let's say in the whole world. You have scientists, you have mechanical engineers, metallurgical engineers, chemical engineers, you have electronic engineers, you have software guys, all working in a team. Who of them will know exactly what you do? So I'm the guy on the right. I'm that engineer. I love my little thing, which is actually honest the truth. I know I love my antenna world. They don't think about it again. So even technically minded people don't think like you do. So they get the understanding that comes from the media, the market, and the impression antennas are no longer relevant. So my story, of course, which is why I make this video, is you need to think about antennas. Because if I look at this picture that I painted for myself here, it's a pretty dire picture that gets driven by the consumer market. And even though I'm thinking about electronic warfare and all those things, it's irrelevant if people have this thing they go home where they spend more than half the time. That's what people do. They don't get any reason to think it's important. You think about internet, you think about iPhone apps or like any app. That's relevant because people keep getting bombarded with stuff about that. But the science, no. All right, so I've painted the picture, I guess. Just different language, same thinking. how far will this aerial go? Now, I get that question quite a bit on our RF shop side of the business. It's not necessarily a very accurate or appropriate question, but it does get asked. People do have a bit of a comprehension that an antenna can get better distance. So they ask, how far can it go? Well, of course, it doesn't work like that. But in the professional world, same question comes up. So same person, so now has to put his professional hat on. He would ask, what's the maximum range I can achieve with this antenna? So he sounds a bit more posh, has the same problem, and he doesn't quite understand. Same with all the other questions I have on the list there. This router doesn't have an antenna. Why would I care? The next one. But you need to make it smaller. So we see so many things getting smaller, hence it's the same problem. How much faster will this make my internet go? Which is the same question. How does it benefit? Can I use my UHF antenna for my 4G? It's a fair question. If you have products like the antennas we get on the bull bars, they look the same, one and the other. So it's a problem that you actually do rightfully so have, that if you can't see the label, the thing look the same. So that makes it very confusing. Can I reuse this old antenna? Also good question to ask. It is possible if their frequency is covered, that might be possible, but maybe there's just deterioration and the material that's no longer relevant. So maybe a valid question, but ideally no. And then, of course, there's so many online options available that are just absolute. I'll not say all of them are rubbish, so don't get me wrong here. Online J-Car Bunnings, they're not all rubbish, but if you look at like eBay, there's absolute rubbish out there. The problem is, though, the price as well. So they get imported in mass from places that are maybe not necessarily the best designer or the best quality stuff. And then that is, again, a thinking that gets rippled through to professional world. So, well, why can't we just get this thing off the shelf? Not always the right thing to do. In EW, probably not the right thing to do as a starting point. In summary, consumer thinking is pushing antennas out of favor. Has been since I started. It still is. Definitely you can see in Australia, but I'm sure it's probably similar in overseas areas as well. Postgraduate interest in this kind of field is very low. And there's very little appetite in consumer space for visible antennas. You don't want to see this thing unless it's a Starlink, because that must bring something good. So they've done something. We want to kind of bring the same thinking back, although it's getting flatter and flatter. And I just saw the Starlink Mini coming out. So even there, they are making it smaller. There must be something that is compromised. I'm sure there is. Now, rather than lament the situation, seize the opportunity. And this is where I think with RF Shop, what we see is definitely something that can be used and should be used. Draw inspiration from other industries. Mining, marine, any industry has lessons to be learned that can be used as well. Now, I got the question in the actual webinar when I did that earlier this week. How can we get the young generation, talk about school children or even students who are already in electronics, to get more interested in defense work or antenna work? That let alone that is quite a tricky one to do. I think I would start with my question again. We need to learn, us as a professionals, start with why. We need to send a message out why we are doing things. Like if there's a little of an interest, you need to get that hook so you can draw them in and then show them once they are a little bit more mature, mid-20s, maybe 30s. Okay, there's more to this. There's something really interesting about what we're doing here. I think for me, just shooting from the hip at the moment, drones is such a nice take on what younger generation can relate to. So use that. Find a way to show something that is really awesome and then say, you know what, this is possible because of an antenna. There's one video online which I actually haven't shared on the screen specifically, but it's worth looking at. Our Red Bull exercise, they made a drone that flies 300 kilometers per hour as a first-person view. A drone racing at Silverstone with Max Verstappen. It's an awesome experiment. It's just something phenomenal. There's nothing functional about it other than it can be done. But it's a cool video, and then that draws a lot of conversations about the next topic. So I just think that's something to think about and to use, that kind of thing. Now, okay, what makes an antenna better? And I think it's getting all the fundamentals right. So if you get all the fundamentals right, then your antenna can be better than something else that doesn't have the fundamentals right. So let me just go into this list and let you think about these things a little bit for antenna design, but more RF in general. And I specifically come from a perspective of the antennas and the passive side of it. So once it exits the power amp, there's still a lot to be done, or before it enters the low noise amplifier, there's still a lot that needs to be prepared before you get it in. So that's really where our speciality lies, is the passive part of what needs to be done. Gee, stumbling here. Sorry. First thing is realized antenna gain. The problem that we see a lot is that the data sheets, the specifications, don't necessarily give you all the information you need at first glance. So the blurb may give you the best gain value. It may give you some information that is half truth, but it doesn't give you the detail. You need to look at the detail. And some examples there is, if you have a radiation pattern, it may say, well, it is a 6 dBi omni antenna, but it happens to be more like 4 dBi. But somewhere in the pattern, if it's an omni antenna, it has a peak that hits 6. Then good, it's a 6 dBi omni. Not if you think that 6 is the whole band, then it's not true. So half-truths is a dangerous place to be. Also, if you have wide band antennas that are just single structures, like a single dipole with multiple resonators, and they say, well, it's a 6 dBi antenna from 700 megahertz up to 3.8 gig, just referring back to the 4G, 5G world. It's not possible that antenna that has this size is going to have the same gain at 700 megahertz as it has in the high band 3.8 gig. Something's going to go. In the low band, knowing the fundamentals of antenna design, it's too small to have a high gain. In the high band, it might be too big, so it's going to have lobing. So it's not quite going to be what you have. Somewhere in the middle, it might be exactly what you think, but below and above, it's not going to do exactly that. But the data sheet, if you just look at the headline, might be different. So look at that. Get the fundamentals right in the design, but also get the fundamentals right in your decision or selection of the product. What we also see is directivity gain according to the IEEE, and realized simulation gain. There's three different selections you could show. It shows the same pattern, but it is a different number. And it could be significantly different because the directivity would be the absolute max because of the pattern only. IEEE gain definition is different from realized gain. The realized gain takes into account losses and mismatches and all those things. So that's the one to go for. That's really the only one that you should look at. And if you get your material selections correct, it will also include the losses of, let's say, if you were to use lossy FR4, that's going to be the one that shows you there's the problem. All right. Now, as I mentioned in the previous slide, if you look at some key antenna fundamentals, the radiation patterns, I did a video on this actually many moons ago. Low gain can be beneficial, high gain can be beneficial. You need to make the right choice. You don't just go for high gain because you can. You need to look at what do I need for coverage. And one of the classic examples is just on a 4x4 or off-road vehicle. You can go for high gain, high as you want, but the problem is if you're at a slope or you're driving under this, it's just going up and down, left and right all the time. The high gain antenna has a very narrow coverage on the horizon, and it will constantly have it will miss the horizon, and you'll actually have this sharp slope where suddenly you are 6 dB gain, 3 dB gain, 0 dB gain. And as you drive, it just jumps all that, and it is very jaggery, and you'd want to avoid that. The same is for marine. So the boat picture that I have is exactly the same problem. If the boat is rocking left to right and your gain is too high, when it's absolutely water is still, it's good, but once you start to move, you sway left to right, you will have a problem. So you need to go for a lower gain antenna to make sure that the softer roll off and slightly less gain, but it's going to be much more lenient as the boat moves. That's going to save your bacon, so to speak. Now, one thing that is, it's come up a few times, and you can easily get caught on this if you are not thinking about this, or if you're not an expert in this field, is we get people who think, well, you need to go low gain in a forest, because low gain, the signal goes up, over the trees, and down again. Now, it doesn't work like that. You have a direct line straight to the other guy. It's not about the wave goes like this, like if you hit a tennis ball or a ball or something. It doesn't have that kind of curve. That's not the way it works. This is just a representation of the signal strength in that direction, nothing more. So there is no up, over, down in the space of a few 100 meters at all. It's a different story if you look at the very low frequency reflections against the stratosphere and all that stuff. That's a totally different science, but this is just relating to your typical 4G, 5G, and Wi-Fi. It's just straight me to you over the next 100 meters or whatever technology it is. Could be quite a few kilometers as well. Right, so another one that is important to take into account is the return loss, voltage standing wave ratio, and what we as designers would think about is the impedance matching. So meaning how well does your circuit then flow into the antenna, and if they are the same value, that flow from one to the other, the impedance on this one and the impedance on that one is very similar, and it just flows through. It's really like water flowing. It's the same logic, it's the same principle. But if there's a big mismatch, this is my system coming in, this is small, this is much bigger, there's going to be discontinuity between the two, and that discontinuity can give you a lot of problems, which is what I show on the slide here. So a voltage standing wave ratio, which is a number that you will see on your data sheets often, 1.2, 1.5, let's say 2 and 3. 3 is already like, no, that's not really an option, but in a lot of the more tolerant systems, not necessarily good systems, that would be a value that people can use. So the return loss, that number there says 20 dB, 14 dB, 9.5 or 6 dB. Good. So those are the numbers that you could see. What does it mean? The next one on the table, now just this table, there's Pastnik has a very nice complete table on their website that you can download. These are just some extracts from that to show. Transmission loss means how much is it that you're throwing away. So you could see there, if you accept I'm going to have a VSW of 3 dB, I'm throwing away 1.25 dB, just like that, just gone. It's gone. No, not to be taken. So you're accepting that you are actually just losing power. Translating that to percentage, 75% of my power is going forward at the 3 to 1. And 25% of my power, I'm just throwing away, reflected back. It's not to be seen again. That is a lot, and that's something to be taken into account. So normally when we do antenna designs, we aspire to get 1.5 to 1. You can see, so we are endeavoring to have 4% reflected. That was 96% is going forward. But if you reach 2 to 1, often people say, yeah, you know what, this is getting close to the best we can achieve. So between a 1.5 and a 2 to 1, that is where we, in fairly, not normal, but normal, normal antennas can do. If you look at the dishes that they use for the astronomy and so forth, definitely that's much better. 1.2 is almost absolute worst case, and then you go even better. So it is technically possible in the very high and very specialist to go way better than 1.2 to 1 as well. Now, don't forget the Smith chart, and this is just a passion of mine. You'll see on my slides and all the logos that we have of RF Shop and Blackheart Technologies, we do use the Smith chart, and we do that for a reason, because it actually is a phenomenal tool. So the example that I have there is just showing you a spiral antenna, which we've done, played with that. It's specifically meant for a Wi-Fi demonstrator, also the one that I use on my dishes. So I have the little example that I'll talk about a bit later. So that little feed spiral in there is this one that I show on the screen. So when you do the initial design, you look at that and you get the return loss from, let's say, 2 to 7 gig in this instance. It's hovering around -10. It's not too bad. I mean, I'm not overly excited, but it's consistent, it's good, it's stable, it's okay. So that's what you get if you just look at it on a Cartesian plot, which is this one, just a return loss. But on the Smith chart, if you see on the next screen, you could see that it actually shows something that you can't see on the rectangular plot. And that's that the impedance locus, the actual locus, yes, is around 110 ohm. So it's not on a 50 ohm. It's not hovering around 50 ohm. So if it was hovering around 50 ohm just consistently, you need to think about something else to do. But this one shows the antenna is very consistent and stable. It's just at the wrong impedance. Okay, so what you do in software, first of all, before you do more design work, you just change the relative impedance of your port that you're excited with. That's all you do, and it's there's ways then to translate that to something that you physically do as well. And you with the new value, which I can see there on the screen, is 110 ohm. Suddenly you have something that is right in the middle of the Smith chart. And going back to the Cartesian plot, suddenly you have an antenna that is hovering between around minus 20 and even better. That then gives you a simple result that is significantly different. As you can see there, the gain on the antenna, it's bidirectional. Like this little spiral here doesn't have a lot of value yet unless it gets placed somewhere where it can be meaningfully directed in a direction. So it's just doing two directions. But if I just went for the original design, it had 2.2, almost 2.26 dBi gain. Was okay, like a dipole, cool, can live with that. But fixing the impedance, which is not even anything on the antenna itself, nothing on the radiator, it suddenly is 3 dBi gain. So I got 0.7 dB gain just by doing some basic fundamentals on the impedance match. So remember your impedance matching. It is super useful. It's super important. The another one is polarization. So the focus that I have here is very much on outside the antenna. Now, of course, you set it up with the antenna, so the antenna needs to launch into a certain polarization. We are used to, if you look at TV antennas, again, going back to consumer experiences, there's vertical, there's horizontal, different areas in Australia, in the world where you go, you would see antennas standing differently. That's the polarization. Circular polarization is a little surprise factor that gets used more in the mining and in the tunneling industry, underground industry. Let me show you why. In a tunnel, you get it's almost just like the only thing that goes is reflections. When you look at the blue picture that I have on there is definitely a link from me to you, so that's a straight link, that's easy. So there could be potentially just direct propagation going forward, but the reality of a tunnel, as you see in the picture that I have there, is it's going around corners. There's always a turn, maybe multiple turns, so the only thing that goes forward are reflections. And then the image that I have in my mind, if I think about this, is just a kaleidoscope. That's why I put that image there. So it's just reflections from all angles. But it's not just a reflection. It's not just going forward and then a reflection like this and this. There's a reflection going like this against the corner, and it turns again. So by the second reflection, everything, the polarization is all over the place. And that is a problem, and that will always be a problem. Now, you can't do anything about that problem, but you can make sure your antenna picks up all polarizations that are there. Now, the secondary problem is every reflection weakens the signal because it reflects, and that makes a loss. And then another reflection makes another loss. So there are many problems in tunnels, and also with all the reflections, it is just that the same signal arrives at the end destination a few times, and like if this is the signal that gets propagated, this is what gets seen at the end. So the processing that needs to be done on this, even if you have a good circular polarized antenna to pick up all the polarizations, is still going to be a problem. So no denying that you have a challenging RF environment, but you can do something about the fact that the polarization goes all over the place. And that's an antenna fundamental that needs to be used to help make this thing at least much better than using linear to linear, because if you have two antennas facing the same polarization, when I launch here, by the time it gets to this one, it's mungled into a fraction in all directions. So you lose nearly everything because you can only pick up those bits that are aligned with your polarization at the receiver end. Another trick with polarization is just on water. It's a simple thing, but you need to know this, and you need to realize this before you can do something about this. So on water or any reflection, if you have a fixed station and a fixed station, and there's water, a body of water in between, let's say it is the ocean, for instance, you have tidal movement that continuously goes up and down. So your reflection between the two is continuously changing, and it is really happening in radio links. If there is no protection, if there's nothing against this, twice a day as the water tide goes through, up and down, you will get a complete and utter cancellation of your signal. And that is a huge, huge problem. However, And the same happens with rocking of boat and devices. So if you have a fixed station here and this boat is moving, it's constantly going through different phases and types of reflections, causing a lot of challenges on your actual link quality because you have reflection interfering with your main signal. So there's many ways to get around this. One simple way is just use polarization, because a slant 45 signal, so if something has this angle, when it reflects, the reflected wave turns in polarization. So suddenly when you are trying to pick up the signal, the main wave that you see from me to the camera, for instance, still comes through. The reflected wave turns, goes in. So your antenna is seeing the reflected wave in cross polarization. Now, if you have cross polarization discrimination, in other words, you are not so effective in your orthogonal direction, which is what the typical dipole or LPDA would be, that helps a lot, because suddenly you can reduce your sensitivity to reflection. It's a simple trick. It's a very powerful trick to use, but you need to know the fundamentals of your antenna design. There, go. Good. Next topic. Losses through material, and this is where I'm going to be a little bit real, because this is from a past experience in my early engineering career. So I had similar to that as spiral antenna that I made, and the task was get a black looking radome in front of the spiral. Cool. Now you have a spiral here, you put a radome on top, because that's just how you're going to cover it. What I didn't realize when I was that young is, like, first of all, black is only achieved by carbon loading the material that we used. Second of all, it's not just going to propagate through this. So it's not just, here's my antenna, I'm just going to hop through the 0.5 millimeter of material that I have in front of it. It actually, being a spiral, the signal propagates through the spiral up to the point where it's resonant, and then it starts to radiate. And that, the longer it travels through this environment with the bonded with a lossy dielectric, the plastic in front, the more it loses the signal. So I had this brilliant antenna. It really performed well, because at the low gain, the low band of the antenna, which is on the outer areas of the spiral, there's nothing left. It was all gone. It was all dissipated in the radome itself. So it's just, that's an extreme example. We see FR4 also being very lossy, but losses in your material is something that you should just absolutely not forget. Okay, cool. Coaxial cables, which is something that obviously RF Shop is very not passionate about. This is our bread and butter. What we do see, if you have cheap suppliers of cable, they mess up the impedance matching, the transformation from big to small. An N-type connector might be slightly bigger. RG316, which I showed there, is slightly smaller. Good connector manufacturers will take care to make sure the transition between the big connector to the small cable is done properly, and it is designed and matched. We've seen a lot of issues with the lower budget cost connectors coming in. They are bad. So, I mean, there might be reputable suppliers, but if you go to eBay, if you go to just DigiKey and you don't know the background of the connector or the supplier behind it, the manufacturer behind it, you may get caught with connectors such as big to small. Having said that, though, there's also an example of a big cable, LMR 600, that gets messed up quite badly. And this, again, becomes really a real case problem that I would have had in my own life. So there's the cable that I show you on the photo. What we saw was, we just thought we'll put a connector on LMR 600. This is a while ago, so we've learned our lesson. Don't worry about that. But we used just a connector from a supplier. And it is basically TNC to LMR 600, and we had massive issues with performance of the cable. Now the other side, as you can see on my picture there, there's actually, this is a Jabo connector. There is a 15 millimeter section extra in the connector from the TNC on the outside, another 15 millimeter piece of metal with something happening on the inside, and then the interface that matches onto the cable. That section there is the impedance matching circuit that actually makes sure that the cable and its properties is properly transformed to what the TNC dimensions are. This connector, the TNC from Jabo, works a treat, like absolutely smooth transition from big cable to the connector. This side, which was the budget connector, didn't work. Caused a lot of pain and headaches in the project, but we learned our lesson, and that won't happen again. We made this cable, the specific one, specifically to keep reminding us of how important it is to make sure you get it right. Okay, now next one, timing. This is one that wasn't in the actual webinar. I just thought about this afterwards, because we do unfortunately see people forget to think about cables. They forget that there's an antenna necessary for a radiating product. So think about it early on. And it might be that the antenna team may need more space around their antenna than you want them to have. They need to know what the limits are. You need to know what the effect is going to be of making a tight space with a very small piece of electronics, and say, okay, and then the antenna just needs to go there. So there's going to be a price to be paid if you don't give the antenna the respect, let's put it that way, it deserves. Also, cable losses can be nasty, so don't forget that the cable decision is important, and the bigger cables might be what you need. The more expensive cables are maybe what you need. So I'm just spruiking RF Shop here quickly while I'm talking about this now. This is just quickly jumping in there on that. All right, next part 2. What makes an antenna better? So just a small piece of a philosophical comment. So technical ecosystem is, could be right, could be wrong, but this is just a very generic way to see a engineering space. You have an application. If it's your phone, it is your phone. If it is a product, then it's a product. Doesn't matter what it is. There is an application of some sort, and you have software engineers and all sorts of people working on the black box there. You have SDR, software-defined radio, some sort of radio interface. So that's where all the conversion from the application to RF world happens. RF front end, that's really where some filtering might happen. You have your PA, LNA, whatever it is that is necessary for your system. That is a common basic diagram of interfaces necessary to get to a point that a lot of people say, well, there we go, it's done. Then the cables need to happen, passive need to happen, connectors, cables, and the antenna. And the part that, truth be told, I'm quite passionate about, the link. The link is really something that, like I said, with the polarization and the way that the obstructions outside of your system can cause trouble. The yellow one is one that gets forgotten, the one that can bite you, the one that you really need to think about all the time. Now, if you have a closed system, if it's a radio link talking from A to B, then of course you do the same on the other side, but I'm just drawing a basic block around the other side because potentially you may be having a radar system, then it's different. You still have up to that point where you have a link, but what happens after that might be different for a radar system, for communication system, all sorts of things. That's just the picture that I show. And of course, most people think the flashy part happens in the application, because that's where a lot of people can relate to. Let's say you want to write an app on your phone. That's the flashy bit. SDR is a little bit more interesting and nerdy, electronic. There are a lot of electronics in there. But what I want to think about is this. Is basically not every task in that ecosystem draws crowds. Like you have this golf player, he has this massive shot and it looks awesome and people are so in awe for that. But if you look at the scorecard, that big shot and the 30 centimeter putt that you missed will have the same impact on the final result. So that's my key takeaway on that's just the message that I want to share. Now, I do think, and I showed this at the beginning as well on my thumbnail, a good antenna is not a luxury. This is not an extreme example, but this is really one where you would say, okay, yes, that is true in this case. It's true for anything. A good antenna is not a luxury. It's a necessity if you want to have a good wireless system, because it's that interface from your electronics to the air. What I do want to say, physics does not change. And that's why the fundamentals that I mentioned is fundamentals that I would have learned back in 1998, 99 when I was in university, and it's still there. There are tricks. There are things that makes the way that we do this different, but the physics doesn't change. Now, if you think about EW, electronic warfare, if you can make a better antenna and RF system, that's the way to outsmart your position. If you think about consumer space, mining space, so forth, it's a way to get more efficient in what you do. It's a way to get a better experience in your wireless technology. Right. How do we apply this? I just want to make a few examples of what we as RF Shop Blackhawk do as well, and just talk about personal experiences. Now, if you were watching YouTube, you would know that I've done this video a while ago talking about artificial intelligence, and I feel like I was left hanging to dry because I tried to talk about something I'm not an expert on. So fair enough, that is true. But the thing there is, first of all, artificial intelligence, it's here to stay, but it's a buzzword that's now suddenly very popular. But genetic algorithms, and then of course a lot of optimization, it's well known in the electronic EM simulation, electromagnetic simulation and design field. And it's not new. When I did my master's degree, did it 2002, that area, the gentleman who was doing studies with me, is now a professor at University of Pretoria, Warren du Plessis. He did work on genetic algorithms. It was not new. So the whole thing of AI is not new, and it's not new in our field either. So is it going to replace us? That's not a topic. That's not what this is about. It is there, and it's certainly something to be looked at. But your base designs, so your basic building blocks, when you need AI to think, okay, what am I going to do? What's the dimensions? They are actually fairly standard design equations. It's not necessarily easy to do, but you don't need an AI system to give you the base concept. Okay, I will need a dipole because it has these features. I need a patch antenna because it needs these features. So where do you need AI? Not sure. It's probably system design, but then there's so many other complications. You still need to actually have hands-on work to be done. I did have, just as an outcome of my experiments back when I did the study, I told ChatGPT to design me a jargon. That's what it came up with. That's why I was totally torn to pieces by the experts in AI, saying it's the wrong tool, it's a language-based tool and everything. I get that. It was just to show what consumers are used to and associating AI with would be ChatGPT. ChatGPT cannot draw an antenna. I know that. And I showed it. The fact that I showed it and people didn't like that, I'm sorry. That's the way it is. It is a field of interest that needs to be monitored closely. Of course, it's there, it's relevant, it's there, it won't go away. But in a niche field like antenna design and maybe even electronics, it needs to be used carefully and not just say, okay, I'll just use my AI and that's the end of it. And it cannot replace the value of hands-on experiments. I am old school there. I guess that's true. But I think hands-on work is going to be so valuable because we need to use these this little thing here between our two ears. We definitely need to use that. Even computer simulations cannot tell you everything that you need to know, which I will show a little bit later. Okay, now then the other exciting one is 3D printing, and I made some videos on that, and it's very relevant and it's very important. So what I'm just showing there is just a news report, not relevant to antennas, but to show colorful prints that were used in a high-end application. The key message is you don't necessarily need to go for the Rolls Royce of 3D printing to get an effect that you need to get. It is changing our world though. What we use it for a lot is prototyping, and you can use it for repairs. Now repairs, maybe you want to use the more specific one for your application, but for prototyping, if you want to get the shape, you want to see what's going on, it is something to definitely look for. Fast product demonstration. Now there's nothing better than having a thing like this and to put it in somebody's hand and say, okay, I'll show you a photo of what I have, but now I could show you in real life, this is what it looks like. And then you can start to tinker and make changes as you go, because suddenly you have something to refer to in 3 dimensions. You could feel it, you could look at it, you could actually say, okay, now I understand what this is all about. Quick turnaround into experiments and assembly jigs. Assembly jigs, so you know, I don't like how this works. Let's make something that supports this, and then I go to the next step. 3D printing makes it so powerful and so rapidly useful to do. Now, a side note, and this is really, why did I do what I do? Like I went on the beach in December and I did a test where I had 4 spiral antennas. So my fingers are tied together. So 4 spiral antennas, and I had 2 Wi-Fi antennas connected to a 5G router. It's not an antenna that will ever be used in the consumer space. But how do you demonstrate EW capability and sciences in the public domain? You use what's available. You use 4G, 5G, and Wi-Fi in my case, because it's available, it's useful, it's relevant, and it also gets used in any industry, so might as well. But the message there is that you can play with the technologies without going into detail about what it can also be used for. So that's a way to share the science, to make it fun. This is basically also how to put the message out to the younger generation. Make it fun and show, look at this quirky thing. It's a weird thing, but actually it has a lot of benefits to it that can be used elsewhere. You don't say that on a public domain, but you would say that then when somebody asks you in person, and it becomes relevant for that specific conversation. Now, okay, just in summary for 3D printing, it's rapid deployment. Product mechanics can be designed. I would certainly say with this parabola that I did, there's no way I could have done this, let's say 5 years ago. This complex structure cannot be done in using high-end machining. It's not in the reason I'm doing it for. It's just too complex. As I said, humans are still in need of sensors. They still want to feel this thing. And a proof of concept, if you want to experiment something, you want to see, does it actually work? Is it going to fly? A computer screen with a simulation doesn't give you all the information that you need to know. This is just a way to do it. So there's the spiral. I have one that I did in orange. It's the same antenna that was used in the slide deck that I showed earlier for my test on the field. It's using 5G, but using spirals. It's never a practical solution for actual consumer applications. There's better ways to do that, but it shows the principle, and we can test the concepts using normal modems. And just get some information out of that. And then 3D printing is definitely simplifying complexities. So as I said, with the parabola, suddenly I could do that with my printer, and I don't have to go to stamped metal. And then what I had to do was change the design from one to the next, and it took me 24 hours to get a new parabola done, where if you had a stamped metal and then said, it's not working, I need to change my shape, it's going to take weeks to go to, and lots of dollars to get it done again by an external subcontractor. There you go. You could see the complex structure. It's actually quite a complicated structure in terms of 3D space, but having it 3D printed, it makes it super easy. So how do we apply the fundamentals? And this is just showing some examples of an antenna. So I'm going to show this little X-band log periodic dipole array in a 3D printed radome. So 3D printing is used actually for a good enough product finish. That's one thing. And then the design itself is done using CST, computer simulation tool, and the actual assembly was based on some learnings and issues and using the Smith chart to learn what we could do better. So first of all, that's the Simpra ultra wideband printed antenna. So that's the antenna on the inside. I see there's measurements on there, but then having it 3D printed, having it in your hand, gives you a context of what it is. Now, of course, granted, that's 120. This is a bit more because I have some space at the back as well, which again, with 3D printing and modeling, you say, well, that's the size, but no, it's not, because I need more space to do some support as well. So I have these screws that I put in there. That's necessary to make it an actual useful product as well. I'm showing that piece of steak because when I got that impedance match, so the middle of my Smith chart, the way that I wanted to work, it is such a satisfying end result. I had a dream that it was just like a juicy medium rare steak, and seeing the grit lines of my steak and seeing the shape is roughly that of a LPDA. I guess you need to be an absolute nerd to see it that way, but that's what I saw, and this is kind of the same sensation. You can see the pattern there. So the pattern of the antenna is not too bad, to be honest. So the rectangular plot showing it's well matched over the whole band from 2 gigahertz to 12 gigahertz. The radiation pattern, which is in this type of antenna, which is consistent over the band, it's the same type of antenna. So it's basically 7 to 8 dBi gain consistently in the forward direction, pointing towards the screen there, over the whole band, which is what I mentioned when I said earlier about if you have a dipole and somebody quotes 6 dBi from low to high, but it's a single dipole, knowing your fundamentals of antennas, you know that's not possible. Okay, so we did the antenna. I'm showing 2 examples on the screen, and we measured it. So you could see the measurement is not quite as awesome as what we had on the predictions from simulation. And often people would say, well, that's it, so be it. Maybe that's the way it is. There's a difference between reality and measurements, or we did something wrong and redo the simulations. But there's also a thing about experience, and I took back lessons. I had to think about this, and then I remembered stuff that I learned from my first mentors and boss back in my first job, Dr. Dirk Baker. And he did a few things on these type of antennas, printed LPDAs, that I thought, well, this is really something I should try. And I instructed the team member who can do much better soldering than me, because there are experts in everything that could be done, and I have access to some people who are really absolutely brilliant in soldering. And I said, okay, we need to look at two things on the way that we solder this on the next PC board. Keeping one as is, modifying the second one so we have a baseline and we do a change, and we could see if the change gets us what we want. That was based on experience only. Experience also by making the mistake as a young engineer and somebody telling me what to do. So now the lesson here is CST is exactly the same simulation result. So CST was correct. You can see on the left was the first assembly. It's not quite what we want to be. You could see the antenna is sort of working, but it's not quite doing what we wanted it to do. The second one says, yeah, okay, this is actually not bad at all. You can see it's below -10, so better than 2 to 1. Yes, prediction said we should be below -15, so there's probably more work that can be done, for sure. But it's a decent antenna from very low to very high. We got the difference from assembly 1 to assembly 2 using nothing but soldering tricks. Okay, at this stage, the recording actually stopped working when I did the work in the studio, but I had all my story covered, so it's all done and dusted. I want to thank you for watching this video, and thanks for watching it through to the end, which is more than 55 minutes. If you have any questions, please do let us know. RF Shop Blackhawk Technologies. We have an email address. Contact us in any way. Otherwise, look out for the next video. We're going to do much more antenna focused contents going forward. More on actual theory and how to apply these awesome technologies in all sorts of applications. So thanks for watching. See you on the next video. Cheers. Bye bye.